All right, I think it's time to get started. So first, hi. Thank you all for coming out to listen to me speak. Seems like there was a lot of excitement and a lot of hype behind this. And let me apologize in advance because you're probably going to be disappointed because I'm an engineer and this talk is mainly for engineers. So you're going to see a lot of screenshots from my IDE. But hopefully it will be informative. With that said, my name is Kaija Keys. I'm a principal engineer at Nextdata, and I'm here to talk to you about using Delta Lake on the data mesh. So it's just a forward-looking statement. Databricks told me I had to put it in here under the impression that absolutely nothing I say to you will be true in this talk, but I mean, that's kind of an exaggeration. It will all be true, but it will probably change by the time you get your hands on any of these things. So by show of hands, how many people are familiar with the concept of the data mesh? Just excellent. Gives me a lot less to talk about. So in terms of what we're going to go through today, it's just going to be I'm going to quickly cover, what is the data mesh, get into how Nextdata implements data products, and also provide an example of attempting to build some data products using Databricks asset bundles. And then maybe some other ways in which you can interact with Delta Lake while building using our autonomous data products. I was going to have you save your questions until the end, but I think it'll be more productive if you go ahead and ask questions as they come, and then we'll try to pause and get to those. So let's see where this takes us. So the first thing is, what is the data mesh? So the founder of our company, Zhamak Dehghani, she wrote the book called The Data Mesh, and this is just a quote from the book itself. It says, data mesh is a decentralized socio-technical approach to share, access, and manage analytical data in complex and large-scale environments within or across organizations. And those are a lot of words, and they're pretty cool words, and that's why I included the quote, but it does make it kind of hard to say that because any sentence is going to be an overly reductive description of data mesh. But the reality is the data mesh is the data products, the communication between those data products, the policies and the governance that goes on top of that. And that's really all it is in a nutshell. But there are some principles that come into a data mesh. One of those is domain ownership. That means we want our people that are building data products to actually be able to build the data products without the impediments that generally come into that process, like getting permission from this group or that group. We want our data platform to be self-serve. We want people to be able to iterate quickly. We want them to be able to define their data products and build them. However, we still need some sort of governance, and that's why federated computational governance is one of the principles involved in the data mesh, because we simply can't live in chaos. And then the last one is data as a product, because ultimately, what is the point of a data mesh without its primary feature, the data products that we want to share? And data is the primary goal of this. So that ultimately means it has to be one of the principles of building a data mesh. So what is a data product? Similarly, it comes with a set of principles. It needs to be discoverable. It's absolutely useless if you can't find the data product. It's a common occurrence in large organizations. You know that there's data somewhere that you want to use, you need to use, but you can't find it. We want it to be addressable. Obviously, once we've found it, we don't want it to disappear. We want it to have some sort of long-lived address at which we can find it. It needs to be understandable. Nonsense helps no one. It's useless. So data products need to describe what they are, their requirements, their constraints, what data they contain. They need to be trustworthy and truthful. That means when they execute, the data that they produce should be the data they say they're going to produce. Natively accessible. So that means you don't need a proprietary new technology stack to access the data when you're using a data product. In an ideal world, you can continue to use the same tools that you've always used to access your data products. Then we want them to be interoperable and composable. That's kind of useless if they're just independent data sets existing in the world. We want to put them together. We make new aggregates from different data sets. And we want it to be valuable on its own. We don't want to have to use random tools and plugins and other things to be able to derive value from our data sets. And obviously, it needs to be secure. Most of us in enterprise scenarios will find that if it's not secure, we can't use it. How does Nextdata implement data products? So Nextdata, our solution, the Nextdata OS, is a solution that exists currently deployed on top of Kubernetes. And its main responsibility is to deploy these autonomous data product containers. So how are they discoverable? Once they're deployed, they're actually registered with our data mesh, and they show up in the UI. If you've seen any of our demos, there's that pretty constellation of data products. But additionally, you're able to search for them, and there are agents that will also help you discover them through their semantic links. They're addressable because they all have well-defined URLs on the internet. They will always exist at whatever your data domain is / that data product. They're secure. We use TLS communication and OAuth for access. I'm not a security specialist, so I'm not going to go much deeper than that. However, they're trustworthy and truthful because they have both promises and expectations. Promises are declarations of the data having been output is the data you expect it to be, and expectations are actually the opposite. Data coming in is verified against a set of expectations before your transformation runs. Also, our data products are natively accessible. All the transformations are just Python transformations or a SQL transformation. So they're the tool sets with which you're currently familiar. You don't have to learn anything new other than how to define a data product in order to use them. And they are interoperable and composable. Data products can use data products as inputs. And you can also see that relationship within the data mesh. So I know I said it was valuable on its own and understandable, and this screenshot is insane, but we'll break it down. Because really this is all you need to make to declare a data product. You're going to specify the compute services that you use, the storage services that you use, the authorization rules, models that it expects to use from its upstream sources, and the models that are performed, along with the actual code for the transformation and any custom promises and expectations. So the next couple slides will be actual details on these things. So when we look here, you see that this is the compute section from our previous slide. And what this is saying is we want to use Databricks compute to execute our transform. So the YAML below you see is actually the configuration that an infrastructure specialist or the data engineers themselves would put into the data mesh in order to use this configuration. Question?
Yeah, you said you're allowed to, right?
Yeah.
What about the managed interfaces?
I can't hear you.
Your interfaces.
The interface?
Yeah. How do you manage those? So what is the rule about that? How do you have to expose the products?
How do we expose the data products?
Yeah.
So the data products are actually exposed on the URLs where I said they're addressable? Or was there more I can answer for you?
Probably a little bit more. So you can have, to me, a lot of data products, you can have them in APIs, you can have them in SQLs, you can have, so what is the rules about how the interfaces are?
So the data products interface is, if we go back to here, and we look at this slide, the data products primary interface is either its input or its output as you define it in the data product model. As a user, if you wanted actual access to the data product outside of that, there is a mechanism for that. That's done through the data mesh UI, but that's out of scope for at least what I was going to talk about today, which is just the process of building the data products.
Okay, I was more thinking about the schemas, so to make sure that the interface are not changing to make that very stable.
Okay, yeah. So stick with me. As I move through here, we should actually get to that. So as I said, this was the declaration of compute services that your data product would use. Moving to the next set is the storage services that your data product would use. It's another thing that would be predefined before you actually get into the process of building data products. Now, our autonomous data products have a set of lifecycle hooks associated with them. One of those is provisioning, one is executing the transformation, and then the other two are executing what we call the promises and expectations. So for someone to implement a storage service, the provisioning step is ultimately going to be optional, but it is useful in places where you're implementing a data product that has a schema. So I think this might be what you were asking about, and this is how we define a model that we would use, or that a data product would expose. This model could be used for either consumption or production. So if we go through this, you'll see that we've given it a name, a description, we've specified a schema, and we've added attributes, and then additionally we've added some semantic links between the different additional attributes. And then lastly, we have some verifications that'll either be executed as promises or expectations, depending on how this model ultimately is used. The type system that we use when defining a semantic model is effectively just Arrow's type system. So we found that that's the most compatible set of types to use across all storage services that we've encountered. Just to check, is that what you were looking for? Okay. So expectations and promises. Those are the additional things that you would define when you defined your data product spec. In this case, we'd say, I expect the model POS sellout when it does not match its type to cause the data product to fail. And the other case here is when I've produced the model products, if there was an error in my transform, I would expect my data product to fail. Now, being in a failed state means that data products that consume from that original data product will stop. So this helps you avoid a cascading chain of failures when an upstream data product makes a change and you don't want that to trickle out into your further aggregates. So, the fun part. So I was trying to build some data products just using Databricks access bundles, and my scenario was very contrived. The domains alpha, beta, and gamma. There's just some tables with some things in them, and then a data product that consumes those two as aggregates. So this was my setup. I used Databricks asset bundles. If you have not used the Databricks VS Code plugin, I recommend you do. It's pretty great. But there were a few tools that I used to make this a little simpler. There is a Python package called Data Contract CLI that allowed me to implement my promises. And if we're going through this, what you'll see is my transform is in the main POI, and the data contract test notebook is actually responsible for executing my products. So what I ultimately had to do, there we go. So ultimately what I could do, can you see that? Is the contrast working? Okay, yeah. So this is, if you're using the data contract CLI package, you can define your model basically in this YAML file with the header, model, and promises. And it turns out it's pretty useful for getting the equivalent of a semantic model into a data asset bundle rather easily. So this was my transform. It's pretty simple. Generated some random data, inserted into a table, called it a day. This was my notebook that ran my promise after I did that. The most noteworthy step is the last, or that step in the middle where it says run data contract test. That will take that YAML file, evaluate it against my Delta table, tell me whether it's good or not. And then you can see my job. Didn't realize I made such a bad screenshot until I did my final review, but we were committed at that point, so that's where we are. Anyway, there's a main task that runs my main transform, and then there's a notebook task that runs my promises. And this is the closest analog I could get to building an autonomous data product. So what I ultimately learned from this is authentication and authorization provided by Unity Catalog are excellent tools. Having the managed compute is also a really great tool. Having the flexibility to use notebooks, wheels, and scripts was also a great development experience. The one problem I really ran into was I was very easily able to build the alpha and the beta data product because I could use cron jobs to schedule those. triggering the Gamma data product to run when both data products were ready involved a level of technical complexity I did not feel like implementing. So I ultimately didn't do that. But one of the nice things about using the asset bundles is if you can run it on Spark, you can run it. And then Unity catalog search, suffices as a good discovery mechanism in this place. But this wouldn't be a fun talk if I didn't tell you how we could do it in a much cooler fashion. So if we're looking at this layout in my repository, I broke it up into a model, a directory with my transform, and a directory with my models, and a directory with my spec. But it wasn't necessary, but it made it more readable. So this was my data product declaration for the original data product, the transform I previously showed you. So if we're looking at this, I went ahead and created a transform that generates code. I scheduled it using this expression, with an hourly interval. I said I wanted to run it on Databricks. I said that my output was Databricks, and I gave it access controls. And then my transform. Actually, it really only changed by 2 lines of code for the most part. If you look at line 14, you'll see that I added an annotation to specify that that's the transformation function, which is a trigger for our autonomous data products to know which Python function to run when it's time to transform. And then, in my write to table method, I got the table name from that output parameter that you can see on line 16, because our data products have knowledge of their underlying storage, so they can tell you those introspective details of how to use it. It's also a useful facade if you're implementing something like like a promotional workflow. And then this was my model. Then my table only had 3 columns. It wasn't particularly interesting, but this was the declaration. So what was different? If you looked at my previous code, I actually provisioned the tables manually. That was a thing I had to do. But using the Nextdata autonomous data products, provisioning is more or less a thing you get for free in most cases. It's just part of the driver itself. Promises and expectations on whether your data is well formed, those are going to be implicit. You don't ever have to write any particular transformation for that. You don't have to say that's a thing that I want. That is a thing that you get. And then the fun part, I was able to orchestrate the behavior between and the gamma transformation between the alpha and beta data products by using this when statement to say, when alpha and beta are done, I want to run. And then our transform runs. So there are some other ways in which we can actually still continue to build data products. So we don't have to use Spark compute. We can use local Python compute if we change the compute service that we specify as our target. And in that case, the only change to your transform would actually just be the removal of the Spark parameter. Another thing that we've seen a lot of people use is actually just using our object store drivers and then using off-the-shelf Delta Lake tools like Delta Lake Python or Polars. And then there's a driver that we have in the works based on Delta kernel RS to actually manage Delta Lake natively within a storage driver. We're currently working on implementing a proper promotion workflow. It's a thing that we've done with Snowflake where we use a shallow clone to promote a table, and we're trying to get the same thing to work within the kernel. But there are a couple pull requests we need to make that possible. And then, really, I'm open for questions at this point.